Good morning, friends. This is Professor a.k.chaubey. Professor Chaubey Physics class under the heading Physics Made Simplest. I am today dealing with some electrical measurements, some laws, etc., which are used to solve the complicated circuits for circuit analysis. So we will talk about the electrical measurements. Electrical measurements. So we have complicated circuits, complex circuits. To solve the complex circuits, to solve the problems of complex circuits, means, what is the meaning of solve? Means to get the value of current in any branch. We use some laws. Say I have a circuit, simple circuit. Say I have a potential source here, say E1. I have say resistor here, E1 potential source, and R1 resistance, and then I have another resistor here, R2, and then I have another cell here. This is the plus and this is the minus, this is the plus and this is the minus. And then we have a resistor here, R3. So such a circuit. We want to know the current in the different branches. We have two potential sources. We have a resistance R1, we have resistance R2, resistance R3. So such circuits, it is difficult to get the value of currents, etc. Simply using the Ohm's law. Ohm's law will not be sufficient. Similarly, we have say, some other circuits, say so we have a circuit like this. Say we have resistances R1 and R2, R3, R4, say R1, R2, say R3, R4, R5. We have say multiple resistances connected like this, and then we have say, a source of the potential, that is the battery or the cell, connected say here like this. So this is the source, this positive, negative, E is the potential. And we want to solve the circuit, means we want to find out the current in the different branch. It is difficult. Using Ohm's law we can't do this, we can't solve. So to solve such circuits, we need some more laws or methods. So that is called circuit analysis. So circuit, this is circuit. Circuit means involving some potential sources, some resistors, some capacitances also, if we have AC type, that is imaginary complex algebra. This is simple, not complex. So this we can solve this circuit. Means we can find out the current in a different branch using some other special laws, and the Ohm's law is not sufficient for this type. So that is why I said that for electrical measurements, to solve these problems, we need something more. So what that something more is there? So I will explain you some laws which will help you in solving or in circuit analysis of these complex circuits. So the laws which are used to solve this, one law is, say we have Kirchhoff's laws. So we have, say, I think it is Kirchhoff, double F. So Kirchhoff's laws. So what are the Kirchhoff's laws? These Kirchhoff's laws are very helpful in getting the circuits, in getting the current in the unknown branch, any branch. So what the Kirchhoff law? So one Kirchhoff law is first Kirchhoff law, that is known as the current law. Kirchhoff gave a law for the current. So what is that? I will state you, I will explain you the current law. And the second law means we have a certain point here, and say certain point, there is one point, say any point A, and there are branches of circuit, current reaching from different sides, current reaching, say I1 current reaching, I2 current reaching, I3 current leaving from here, and let's say I4 also current reaching, leaving here, and so on. So there are, at certain point, there are many branches, wires connected, means current flowing in this. So current are reaching to a certain point A, current reaching at a certain point and also current leaving. This must be equal. Must be equal. What do you mean by this? Means current reaching, if it is taken say positive, then current leaving is taken negative. Means say I1 current reaching plus I1, current reaching plus I2, and current leaving minus this say direction I3 minus I4. So what does it mean? At any point, at any junction point, in a circuit, there is no, what is the law? There is no accumulation of charges. Means charge is not collected at any point. Charge is collected across the condenser, capacitor, but at any certain point where there are many wires connected, some currents are coming, some currents are leaving, there cannot be any accumulation of charge here. No charge here. Means whatever current is charge approaching, the same must be charge leaving. It means the total current approaching, total current leaving must be equal, or the sum of all the currents must be zero. Sum of all the current must be 0. Means if I write, say, current reaching, say, I1 plus I2, then current leaving minus I3 minus I4, this must be 0. Total sum of the current must be, because no accumulation of charge is not collected at any point. So whatever charge reaching, the same must be leaving also. So that is the total current in the circuit must be, or the positive current must be equal to, means current reaching and current leaving must be equal. Current reaching and current leaving. I wrote at a certain point also current leaving must be equal. Current reaching and current leaving. Or the total sum of current must be 0. Or mathematically I may write summation of the current I may be 1, 2, 3, 4. This must be 0. Means total current at any point, any junction point in the circuit anywhere, there is no accumulation of charge. You can understand this way. Charge is not collected at any point. There is no source to collect. Capacitors, they have capacity to store the charge. So current reaching there, current leaving must be, algebraical sum of the current must be 0. That is, the algebraical sum of the current must be 0. Or the current approaching, current leaving must be equal. So this is the Kirchhoff current law, and this is very useful for circuit analysis. Means to get the unknown current in any branch. So we will be using this Kirchhoff first law, Kirchhoff law of current, to solving the problem. There is another law which is also very useful. That is the second law, Kirchhoff's second law, is voltage law. Well, one was current law, the other is voltage law. What is the voltage law? What do you mean by the voltage law? Say that is the, we can have a circuit, say, many potential sources or many resistances like that. Or I start from some simple, first is a simple circuit that I have, say, a source of potential, battery, many cells connected together, suppose. This is the positive end, this is the negative end. This, the battery or the cell or the combination of cells is connected across resistance R1, say, R2, say, R3, say, and we have some key also. We have a ammeter for current measurement, and the current is flowing, say, in this direction, like this. Current is coming, current is leaving like this. So this is the current direction, I. So a battery source, say, a source of potential, that is battery, means EMF source. Say suppose E is connected, EMF E is connected, say, to a circuit involving, say, three resistances R1, R2, R3. EMF source, E is the source of EMF. So there may be more than one, 2 or 3 sources also, multiple sources also. So then we have to add all these, E1, E2, E3, so EMF sources. The E is the source of EMF, means maybe several sources where then E is the total EMF of all. Means, all means there can be say E1, E2, etc. So that is E is the total EMF, means they are in series. So this E by E may be with plus minus, means if their terminals are opposite, it will be minus. One source is say having plus and say current flowing say anti-clockwise, the other source having plus like that, current flowing clockwise, then one is positive source, other is negative, means current going in reverse other direction. So then the EMFs are, one is plus, other is minus. So E is the total, E is the source of EMF, or E is the algebraical sum of all the potential sources. And then B1, B2, B3 are the potential drops. B1, B2, B3 are the potential drops across the resistances. Then the total EMF applied. This is the EMF which is giving this voltage. So obviously the total EMF must be equal to the total voltage. So that is the E must be equal to V1 plus V2 plus V3. Or if there are many EMF sources, several EMF sources, then summation of EI must be equal to summation of VI. That is the voltage drop across the various elements added together with the algebraical. Summation means plus minus, and EI means all the EMF sources. So that is the E1, E2, E3, etc. must be V1, V2, V3, etc. So summation of all EMFs. If this is the opposite, this will be E1 minus E2. So this is the algebraical sum. Remember, algebraical means with plus and minus. So this is the voltage law of Kirchhoff, given by Kirchhoff. And to understand this Kirchhoff law more clearly, we can use some circuit actually. Let us take some circuit and discuss that circuit. So I have a circuit diagram. I draw a circuit diagram. Say this circuit is, I draw a circuit like here there is a resistance R1 and here a junction, and here there is resistance R3, and here there is resistance, no R3, there is R1, R2, and a current say I2 in this branch, a current say I1 in this branch, and say a current here, and say a battery source here, plus, minus, plus, minus, plus, minus, plus, minus. So this end the plus, this end the minus. So current going like this. That is I1, current is starting from like this. And there is another source here. Say this is a minus, plus, minus, plus, minus, plus. So that is a plus here and minus here. So this is a E2 and this is a E1. Current is here in this branch, I1, and current here, this is plus sign, this, so current here is I2, going in this I2, I1 going this side, I2 going this side, and here current I3, obviously I3 will be equal to I1 plus I2. By the Kirchhoff current law, current coming and current leaving, both must, algebraic sum must be 0. So I3 will be equal to I1 plus I2. That is the Kirchhoff first law. Using Kirchhoff current law, I can put some number here. Say this is A, B, C, and say D, and say E, and say F. So Kirchhoff current law at junction C. Here, current approaching, current leaving must be opposite side. Kirchhoff current law at junction C gives us I3 is equal to I1 plus I2. So the current flowing in this R1 resistor, this I3 equal to I1 plus I2, two currents. No accumulation of charge here. And this voltage is sending current in this direction. This EMF sending current in this direction. So you can see that what is this circuit, you can say. What is the circuit here? Applying Kirchhoff voltage law to closed loop, say. Now we will apply voltage law. Apply voltage law for the loop. We divide the whole circuit in two loops. One loop is this, current flowing like this. Other loop is this, current flowing like this. So for loop this A, B, C, F. What we can write for this loop? The potential drop is here in this circuit and potential applied is this, E1. So obviously that E1 must be equal to E1, potential applied, E1, this is plus, sending current like this. So in this is the resistance. So what the potential drop here? That must be equal to, so E1 must be equal to I1 plus I2 into R1. That's this, in this loop. Potential applied must be equal to the voltage drops. So EMF total or summation of EMF must be 0. Means this side E1 minus I1 plus I2 R1 is 0. Or I can write directly E1 is equal to I1 plus I2 into R1. Okay? And now we see the loop, other loop, this loop. This loop current sending like this. This loop current sending like this. This. So, for the loop, C, D, E, F. For this loop, current flowing through this resistor is say same I3, but this loop has got a resistor R2 here and this voltage source. Remember that current flowing here in this direction, and this current is like this, in this way. So in this current flowing in this direction, and this current flowing opposite. Both currents are opposite each other. So we can see that voltage drops. I2R2 here. This is current is I2 here. So I2R2 is the voltage drop here, and I1 plus I2 R1 voltage drop here. But both the voltages are opposites because current directions are opposite. So we can write for this loop I2 into R2, this voltage drop, and this E2 is, say, current flowing like this. E2 is the voltage here. So both are opposite voltages, direction wise. And here here current is I1 plus I2, I1 plus I2 to R1. So this current is same direction here, this current here, this in the loop like this. But current flowing through this in the battery, here current flowing is the minus to plus. So this current from plus like this, and this current both are opposite. So I2 into R2, and what the voltage source? This is minus E2 and plus I1 plus I2 into R1. This is, so this total potential, the potential, applied potential must be equal to the total drop, so that it must be E2, that is the applied voltage must be equal to potential drop. Or you write like this equation, that E2 is the potential EMF source which is generating the voltage drop across this. So what is the voltage drop generated across R1? I1 plus I2 into R1. What is the voltage drop generated here? R2. And this, so summation, or you write E is equal to V. Summation of E is equal to summation of V. This was voltage law. So that summation of V, here we have only one source. So that is E2 equal to summation V. Summation V means the total voltage here. That is I2 plus I1 R1 plus I2 into R2. Total EMF must be equal to total voltage drop. So these current law, earlier we wrote, and voltage law. These two equations can be used. These two equations can be used. That is E1 is equal to I1 plus I2 into R1. This was earlier. So for this circuit and for this circuit, these two equations can be used to get the current through. If we want to get the I1 I2 separate and then current through this, these two equations can be used. And so this, whatever problem you can solve and you can get the unknown from this. Whatever, something is, one thing may be unknown, R1, R2 are giving you, even E2 are given. Maybe one current is known, that you can calculate the other current using this. So these two equations. So using the voltage law and earlier current law we have also. Current law was I3 is equal to I1 plus I2. So that we can use. That gives us, in this way, using the Kirchhoff current law, Kirchhoff voltage law, we can write some algebraic equations and we can solve them to get the unknown. One thing must be unknown only one unknown parameter, maybe one current in any branch that we can get. So Kirchhoff's laws are very useful to solve the circuits for the DC circuit. This is so far DC. When we use AC, it will be complex algebra. That is, the I will come, virtual, complex number will come. So this is the Kirchhoff law, and we will apply Kirchhoff laws to solve the various circuits. That is, circuit analysis can be done. Now I will tell you here another important say method of circuit analysis that I call Wheatstone's bridge. You see, Wheatstone's bridge is another method of some circuit analysis, complex circuit analysis. We can do complex circuit analysis using Wheatstone's bridge. So what is that bridge? So that is, I use a resistance This is resistance P, and another resistance Q, and I use another resistance here. Well, you can write that R and this branch S, R, S, and so this is here we connect a battery, or here we connect a battery anywhere. We can connect a battery at 2 points, suppose here. This is the battery, a key here, this key to press, and then and here we connect a galvanometer, a device to detect the current. So this is a circuit, say A, B, C, D, A, B, C, and D. 4, and this is a source of EMF, E. And this is the K key. And of course, the P, Q, R, S are 4 resistances, and I have the current here. Let us say I1 current here, and I2 current here. And this current is now coming here. This current may be here, divided, some current may be here, and some current may go here. Here also, this current, some current may go here, and some current may come here. So this galvanometer, I1, and I call the I2, I say this is the I3, and this is the I4. So current here is I2 minus I4. Current here is I1 minus I3. So this circuit is called Wheatstone, is the name of the scientist. Wheatstone bridge. There are 4 resistances, P and Q and R and S. And this galvanometer is to detect whether a current is flowing in this, means current, if I3 is more than I3 minus I4, current will flow here. Or I4 is more than I4 minus I3. So some current will flow here. So galvanometer current is indicator that point B and D are at the different potentials potentials if V is more than Vd, well, current will flow. From B to D direction. Opposite will be the case if Vd is more than Vv, current. Here current will be I3 minus I4. If Bd is more than Bv, current will flow. from D to B and I4 minus I3. Current will be, because this is more than current flowing like this. Okay. Now let us see, in this bridge, when VV and VD are equal, the potentials, both potentials are equal, no current will flow. Through galvanometer. So galvanometer will not have any current if the potentials of these two are same, because current flows only when there is potential difference. Potential difference means force. If force is there, so charge, and charge will flow. If the force is not there, charge will not flow. Charge will not flow means current will not flow. So if no current here, means I3 and I4 are equal. So resultant current will be zero, means the potentials of this condition is called, this situation is called bridge is balanced. Means when no current flowing here, this current, no current flowing here, no current flowing here. Galvanometer reads zero, and galvanometer reads zero. No current to galvanometer means balanced bridge. No current through galvanometer means current in AB and BC is same. Let us say I1, because no current flowing through the galvanometer, so no current, no branching of current. So I3 is equal to 0, I3, I4 0. In fact, I3 equal to I4 equal to 0. So the total current I1 here is also I1. Also, no current through galvanometer means here also I4 is 0. Current, also current in say R and S are same, equal to I2. That means current I1 here, current I2 here, I2 here, I1 here. What does it mean? The potential of A and B is equal to potential of A and D, because there is no potential difference, no current flowing. So potential V across AB must be equal to V across AD. That is I1 R1, the I1 P, or R1 you can say, I1 into P is equal to here I2 into R. Good. That means I1 upon I2 is equal to I1 upon I2, R upon P. Similarly, when bridge is balanced, no current flowing through this, total current going I1 there. Similarly, potential across BAC, VBC must be equal to DC. That is I1 into Q must be equal to I2 into S, or I1 upon I2 I1 upon I2 is equal to S upon Q. What does it mean? From the equation this, I put number 1. From the equation this, number 2. Number 1 and number 2 are same, I1 upon I2. This means equating 1 and 2, both 3, check, 1 and 2, the same thing. That means R upon P is equal to S upon Q, or P upon Q, I write P here, is equal to R upon S. So that is 4 arms. A circuit made like this, 4 arms of resistances. Well, this may be suppose unknown. This may be unknown, and these may be known. This. So what we call? We take out P and Q from, we put here some resistance boxes. From resistance boxes we take some value P and Q out. So we take, say, and P and Q are called ratio arms. R is known resistance, S is unknown. So if we are given some resistance wire, we can connect a resistance wire here, or we are given a resistance of any shape, we want to know that we can connect it here. And we can make circuit like this and just adjust the value of R so that no current flowing through galvanometer. Fixing P and Q, we can fix a P and Q. Ratio arm, say we take P and Q, say low resistance, we start from low resistance, say P is equal to Q is equal to say 10 ohm. We take both resistance 10 and 10 ohm, low resistances. And then we see what value should be R so that keeping X constant, no current flows through this. Means we have some key here also. So when we press this key, press the key, and we see galvanometer current 0, no deflection. So P and Q both are. So then P over Q, R over S. S is unknown. So R over S is equal to 10 upon 10, means 1. So that means S will be equal to R. That gives the some value. To get the more accurate decimal point, what we do? We change P or Q, we take, increase the ratio, that we take say P is equal to say 100 and we take Q is equal to 10. So P upon Q is equal to 10 is equal to, now we take P upon Q is equal to 10, R over S, R over S. So S is equal to now R by 10. Means we have to take out here resistance R such that S is R by 10. It is said R by 10 S, means here the ratio is S over R 1 by 10. So we get 1 by 10 means decimal first point. The value of this will be 10 times of this. R will be 10 times of S. So whatever S we unknown, here R we have 10 times. So it means we will get, here it was 1, here is 10 times. So here it was S is equal to R. Here S is equal to R is equal to 10 times S. Here R was S. So 10 times means decimal first point. But remember, as we increase the resistance ratio arm, the bridge becomes less sensitive, because more resistance, current becomes small. Then the fluctuations, small fluctuations are not taken into account, and so bridge is not so much sensitive. We take, say, P is equal to 1000 and keeping Q as a 10. Then 1000 over 10, P over Q is R over S. So is R over S. So S is now, or R is now 100 times of S. So we have to take here resistance from resistance box, which is 100 times of this. So we get now S is R upon 100, means we get decimal point, second point here. It is 1 by 10, it is 1 by 100. S is R by 100. So whatever R we take from here, it's 1 over 100 is S. So that gives us the second decimal point. In this way, S is calculated up to second decimal point. So this method, Wheatstone's bridge, is very sensitive when all resistances are nearly equal. That gives more accurate result. Otherwise, sensitivity decreases if in the 1 arm resistance is 1000 times of this. Here both also P, Q more 1000 times. So when ratio is too large, the sensitivity decreases, because current in this arm becomes very small. So small current fluctuations you can't read. Fluctuations cannot be taken into account. So sensitivity of bridge is only when all the 4 arms are having nearly equal resistances, so the ratio is 1. Then current fluctuations, small fluctuations can be read. So Wheatstone's bridge is very good to get unknown resistance like this. This is also used in the laboratory. We do the experiment to get the value of S, and then by measuring the radius, if it is wire, we get the specific resistance also. So this method is good to calculate a specific resistance of any resistor material is measured by measuring the S, because you know that S will be rho L into A. So if length of wire is known, A area is known, rho can be measured. Rho is the specific resistance, that is A into S divided by N. So A is the area of cross section that can be calculated by measuring the radius of wire. If the resistance is in the wire form using a screw gauge, and L can be measured by using a scale, and S is already measured. So this gives the specific resistance also. Then remember, this Wheatstone's bridge can be also used. In the laboratory we can design an experiment also to measure the resistance of galvanometer. Here it was wire. If we want to measure the resistance of galvanometer, means to measure, this is to measure a specific resistance, and to measure the resistance of galvanometer, this same experiment can be designed to measure resistance of galvanometer. What we do? We connect this galvanometer at the place of S, that is unknown resistance. So galvanometer is connected here as unknown resistance. And here we connect simply a key. This is a key. So that when we press the key, the potentials are same. V and D means bridge is balanced, no current will flow in this arm and no deflection of this galvanometer. So that is the galvanometer deflection. Galvanometer reading remains constant. So what we do by pressing this, when we take resistance here R, such that P over Q is equal to R over G, and we press this key, if the galvanometer reading remains constant, means no current flowing in this arm and the bridge is balanced. So keeping the galvanometer, change the resistance such that galvanometer, when pressing this key, the deflection doesn't change. That gives the resistance of galvanometer. So galvanometer reading remains constant. Using this constant reading of galvanometer method, we can measure the resistance of galvanometer. The Wheatstone bridge, you see, also used another experiment you can design, that is called in the laboratory meter bridge experiment. What is the meter bridge experiment? Meter bridge, you see, meter bridge is also an experiment. We design the circuit, that is a meter bridge, means we make the Wheatstone bridge as a meter bridge, means we have a 1 meter long wire at the two ends. And here we have a strip, thick strip, having no resistance, and we have thick strip here also, copper strips. And then here we have a gap, and then we have a strip here. We have one terminal here, we have one terminal here, we have one terminal here, one terminal here, and then a gap. There is also a gap, a strip of copper, so zero resistance. This 1 meter wire, 1 meter resistance wire. And here we connect resistance box, say this resistance P. Here we connect a resistance box, this resistance is Q. And here we connect a galvanometer through a variable key. So where we touch this, that point becomes, this is say, connect the battery somewhere here. Say here we connect the battery because this is arm. That is the battery here, means this is the point A, this is the point B, that is also B, this is also B, and then C, and then this is A, so this is also A, this is also A, like this. And this is B, and this becomes, say, D. When we connect this jockey, that is variable key, in the wire, this point becomes D, wherever we connect. So resistance of this wire means proportional to length. So L1, resistance of this wire, L2, and this point D where no current flowing galvanometer, no current through galvanometer here. Then this is called bridge is balanced. So by getting this L1, this point D, L2, we get P over Q is equal to L1 over L2. So this method, the same Wheatstone bridge is made here. This is one arm, second arm, third arm and fourth arm. Battery connected here and galvanometer. So this is the construction of meter bridge based on principle of Wheatstone bridge. That is possible to get. So in this way we get the, and this can be also used here. This is not, you see, this is used to get the P and Q, any resistance here, and L1, L2 is known. Or we can get the specific resistance of meter bridge wire. Object can be any. This is possible. By knowing this L1 over L2, P and Q is known, this is same wire, so we can get the resistance of this much length, and that is proportional to the length, resistance, and the inversely to area. So when we get resistance by this, and same we change B or 200 times, 1000 times, we get the resistance of this wire, because both resistance is proportional to length. So resistance of this wire is X into L1. X is the resistance per unit length, like that. So that gives meter bridge is based on the principles of Wheatstone bridge to get the specific resistance of any resistance while you can connect. You want to have, say, unknown resistance, then you connect in any branch where P and Q connected, you can connect, say, unknown resistance as there. Like that also. Means we need four resistances, P, Q and R and S. So this way, Wheatstone bridge principle is used in the laboratory to get the unknown resistances, to get the special resistances. So meter bridge is also based on that. And then there is a post office box, which I think now post office box is not used. We got telegram, it was used in the telepathy, telegram. So telegram department is finished now, so I will not talk about that. Friends, next time we will meet, we will solve some problems based on the Wheatstone bridge, based on the Kirchhoff law, etc. So today I will stop here. Friends, thank you very much for listening to me.